This is section 6.1, reflection symmetry. So the first thing we've got there is definition of reflection symmetric figure, and then symmetry line is also in that definition. So that's on page 308, so let me flip to that here. Okay, so that says a plane figure F is a reflection symmetric figure if and only if there is a line M such that if you reflect over M some point F, it's going to equal F. And then it says the line M is a symmetry line for the figure. Okay, so let me kind of draw this out here. So say we had some kind of house. That is a horrible looking house. But something like that, where maybe you got like a door here, a couple windows. Okay, imagine that's a much better picture. Okay, so what they mean here for a figure that's reflection symmetric, figure is just like a picture. So symmetric is basically you could like fold it in half. So like say I've got some line that kind of cuts right down the middle here. And again, imagine that picture is a little better. But some line that kind of cuts down the middle, that if I took this half of the house and folded it over, it would look exactly like the other half of the house. They kind of have another picture in the book there on page 308 of a lion that you could do the same thing, where if you folded it over, both sides would be exactly the same. So this full house here would be a reflection symmetric figure. And then this line here that we're flipping over, that's what we call our symmetry line. Okay, so our symmetry line is basically like our line of reflection that we had before. So if you can take and kind of fold that shape over, it's reflection symmetric, and then your actual fold line would be your symmetry line, the line that splits it directly in half. Next thing we've got here is the flip-flop theorem on page 309. So you can either use that picture there, or there's another picture in the book of a couple flags you could use too. So the flip-flop theorem says if F and G are points, and we do a reflection over L, so some line L of F, we get G. Then if we flip over that same line L, we flip G over, we get F. And then the other one basically just says, instead of points, it references that as figures. So if you flip one figure over the line, get another one, you could also flip the other way and get the same picture. So what it's basically saying here is if we took, say we took this picture G, flipped it over this line L and got F, we could have also started with F, flipped it over that line L, and got G. So basically all this theorem is saying is you can flip either way, and both of those pictures will still match up with each other. You could start with F, you could start with G, either way works. Okay, next thing is segment symmetry theorem. So we've got a segment here, and then on page 309 is our definition, or it's a theorem I guess. So it says every segment has exactly two symmetry lines, the line containing the segment and its perpendicular bisector. Okay, so a lot of times when people are doing this one, they get the first one right away. So one of the lines here would be basically going like that. Hopefully you can see that yellow, okay. So one of the lines would basically be like a perpendicular bisector there, right? Because if you take this segment, flip it over that line there, you get the other half of that segment. Now the one that people have a hard time with is you could also have a symmetry line cutting right through that segment, because if you have your line going through that, so like a line through PH there, if you flip that segment over that line, since all of the points of the segment are on that line, when you do a reflection of it, it's still going to be on that reflection line. So that's also a symmetry line. So anytime you have a segment, you're going to have two. You're going to have one that's the perpendicular bisector of the segment, the yellow one there, and then the other one is a line going through that actual segment. Okay, so don't forget about the one that's going through. A lot of times people forget that one. Okay, next thing we're going to jump to is there's an example sheet, so it should be on that Google site there in the extra handouts or section or something like that, whatever it says. So here we're supposed to write a proof that the line that contains the segment PQ is a symmetry line for PQ. And then we're given a segment, and then we are supposed to prove that the line PQ is a symmetry line for the segment PQ. Okay, so I set this one up on the back here. I don't know if it's scanned or not onto the PDF thing that's uploaded on the Google site. So if not, just write this down. If it did, then just ignore that. So what we want to do is we want to fill in our missing stuff here. So what we know is we're starting with some sort of segment. So we were given, let's draw a picture here. We're given some segment PQ, and they told us that was our given. So I'll write that in here for given. So given segment PQ. And then what they say here for our conclusions is basically if we take and we flip over, so let's see this here. If this is our segment here and we've got some line going through that as well, so like that, if we flip over that line, if we flip P over, since P is on the line, it's going to stay as P. If we take Q and flip it over that line, since again it's on the line, it's going to stay at that position Q. So this is going to be definition of reflection. Because that's when we take a point that's on the line, flip it over, and it's still on the line. That's part of that definition. Okay, and that works for both the P and the Q. Now the next thing here is we are going from the points being individually flipped over those lines, so the P being flipped over and the Q being flipped over, to now connecting those to a segment, so the segment being flipped over is still the same segment being flipped over. So if you remember back to last chapter, this is going to be our figure transformation theorem. Because in that theorem, basically you're going from individual points being flipped over to some line to a full figure, in this case a segment being flipped over that line. And then the last one here, so our justification is already filled in for us, definition of symmetry line. We have to fill in the last thing on the conclusion side, and we can always find that by what we're trying to prove. So if we look back on our other side here, what we are trying to prove is that the line PQ is a symmetry line for that segment PQ. So that would be our last thing on our conclusion side, is just exactly what it says for the proofs. So line PQ is a symmetry line for the segment PQ. Okay? Alright, what's the next thing here? Another theorem. So now we've got side switching theorem that's on page 310. So that says if one side of an angle is reflected over the line containing the angle bisector, its image is the other side of the angle. Okay, so what they're saying here is if this line, so here's kind of a picture, if this line here, BD, or it's not really the line, the ray, BD is the angle bisector, which we've got written here, then what it says is if we take one of these angles and flip it over this line, so whatever, this angle is here, if I take that angle and flip it over that angle bisector line, then this angle would be a reflection of it. Okay, so basically I know whatever this angle is, this one's going to be the same thing, and they're going to be reflections of each other. Okay. Now the next one here, angle symmetry theorem, kind of goes right along with this side switching theorem. So it says the line containing the bisector of the angle is the symmetry line for the angle. So what this one is saying, and I'll just draw an arrow up here, what this one is saying is if this line here is an angle bisector, which we know it is, it's also a symmetry line. And a lot of this stuff we've kind of talked about before, like we've talked about those angles being the same, so that's we've kind of been talking about side switching theorem without actually giving a name to it. The only thing that's kind of different here is we're naming this angle bisector as the symmetry line, but symmetry line is kind of similar to a reflection line. So really it's just kind of building on the knowledge we've already done. Okay, so the next thing here is activity 2 on page 311. So if you read through that, it says draw a circle with center O and all of its symmetry lines. So I'm going to grab my compass here and draw a circle. Okay, so I'm going to start with the circle. Okay, so what it wants me to do is it wants me to draw in all of my symmetry lines. So basically symmetry lines are lines that I can fold on and get the same thing on both halves. So if I kind of think about this like a pie, I could take and split up and down this way. So if I fold that side over there, both of those sides would be the same. Maybe I want to split it in quarters. Going this way, I could also have a symmetry line going this way. And then, like I said, you could do like a pie, split like this way. And really, the whole point of this activity is you could go and make like an infinite amount of lines, and they would all be symmetry lines for that circle as long as they're going through the center. Okay, and that's actually our next theorem here. So it says for the circle symmetry theorem, it says a circle is reflection symmetric to any line through its center. So really there's an infinite amount of lines here that could be symmetry lines for this circle. The only stipulation is they go through the center. Okay, so there's a whole bunch of symmetry lines for circles. Okay. Alright, next thing here, we've got symmetric figures theorem on page 312. So that says if a figure is symmetric, then any pair of corresponding parts is congruent. Okay, so that's kind of like what we've talked about with reflections before. So if we take some shape and flip it over, then the parts match up. Same thing works with symmetry. Okay, and we're actually going to do, in the next example here on the sheet, it goes right along with that. So what we've got going here is it says this figure is reflection symmetric over the line from S through W. So basically we've got a line here splitting that, and that's going to be a symmetry line. And the first thing it wants us to find is if we take those points, so S, T, U, V, and so on, and flip them over that line SW, what we get back out. Okay, so like if we take S and flip it over, so S is actually on that line, right? So when we flip it over, we're still going to be at S. Then we just go through, and you can fill them in down here in this solution area. Then we just go through those letters. So like T, if we took T and flipped it over that line, that would be at Z. Next one is U, so if I took U and flip it over, I'd be at Y. V, if I take V and flip it over, I'm at X. Next one is W. If I take W and flip it over, well, W is on that symmetry line or like a reflection line, so W is still W. Next one is X flipped over, which would take us to V. And then Y flipped over would take us to U. And then the last one, Z flipped over that line, would take us to T. Okay, so it's really similar to just our reflection stuff, and that's what they kind of say there. Okay, so then based on that last theorem that we had there, symmetric figures theorem, we now know that the parts match up with each other as well. So like angle T here, if we flipped it over, it would be congruent with angle Z. Okay, same with angle X. If I take angle X and flip it over, that's going to be congruent with angle V. We've also can do that for segments, so like segment SY, so from S to Y, if that was drawn in, that's going to match up with, if I look at my letters here, S matches up with S, and Y matches up with U, or you could kind of draw it in here as well, so SU, or you could write it US. TU, so if I look from T to U, T flipped over is Z, or I could look here, T and Z match up with each other, they're both in the second position, so I know T is going to match with Z, and then U is going to match with Y, so ZY, or I could look in here, U matches with Y, both in the third position. Next one's Z to S, so that's going to match up with T to S, because the Z and the T match up. And S is going to be in the same spot both times. And then the last one is W to Z. Well, I know W is going to stay as W, because that's on that line. And then Z matches up with T, So WT for that segment. So it's really, really similar to the reflection stuff we've done before. They're just calling them symmetry lines instead, which is the same as our reflection lines. Okay, so that is it for notes. So that's your book page there. 312, 1 to 18 all. There is a sheet that goes with it, so if you want to print this sheet out and write your answers on that, you can. If not, just kind of draw them in. Either way is fine, and there is 2 sides to it.